Once you obtain the solution for your model, the next step is to examine the parameter study, like changing the model parameters and see the response looks okay, like a feasible or makes sense, okay, or intuitive. So for example, assuming that my rimless wheel model can generate the periodic step forward down the slope, and my parameter study will be like, what if I increase the slope? Is the rimless wheel model walks faster? Or if I made a spoke angle, the interlag angle here to alpha, if I increase the alpha, what would be the change? Like if I have a more dense spoke or versus the sparse spoke, which one walks faster? Well, intuitively, if I, um, make the extreme case for the alpha is really, really small, it's gonna be pretty much similar to the disk. So it'll really rolls down fast. So I would guess the greater alpha will slows down the walking for the rimless wheel. And what will happen if you increase the radius gyration, which means if you have a broader distribution for the mass, not versus the point mass, what will happen? Well, for the larger distribution, the further distribution from the center may increase the moment of inertia. So maybe once it kicked into the rotational motion, I think it gets faster. Maybe my intuition could be wrong. So you can think of what would be the change for varying the parameters, like what would be the greater loss would happen for before and after collision is going to be, slows down those omega or what. So after changing those parameters, actually you can solve it by, you can actually examining by solving the equation. So this is the theta and omega solution for the equations of motion. And I know that for steady state gate, I know the final, like a before collision solution for the theta and omega is going to be alpha and omega minus, which is omega naught divided by the eta, right? So by plug that into this solution, you can actually obtain the relationship for the omega naught in terms of the other model parameters. So I would strongly recommend you to find it by yourself. But to give you the answer, your omega naught is gonna be a function of alpha and gamma and sigma square and the eta square divided by 1 minus eta square. So look back how we define the eta and the sigma. Eta is the ratio between the before and after collision, the loss factor. So it's a function of alpha and the radius of gyration. And sigma square is what we defined in the very beginning when we obtained the equations of motion. It's going to be a function of radius of gyration. So if you plug it in, you will have a little bit more complicated form. And to make this one simple, for the point mass system, your radius gyration turns out to be 0. So simply what I could have is a simple like a 4 alpha gamma cosine square 2 alpha divided by 1 minus cosine square 2 alpha. So definitely here, I only have a gamma term here. So for the greater slope, I will walk faster in a manner of a square root. And how about the alpha? Alpha is also proportional to the speed as a order of square root weight. But I also have alpha term in the another denominator multiplication factor and also even numerator and the denominator. So actually, you should actually draw it, and then if you draw as a function of alpha, your omega naught is gonna be say, you know, according to my intuition that smaller alpha give you the faster speed, and larger alpha, the sparks spoke will slows down the speed. How about the radius of gyration and the eta? You can also plug it into the your equation and then see if your expectation or anticipation will actually fit into your results for the model. At some point, maybe your anticipation or prediction might really match with the model results, but at some point, maybe your expectation might be pretty different from what actually model gives. So in that case, maybe your model has a assumption error. Maybe you made a too simple, like a too much simplification assumptions applied, or maybe your thinking logic have some missing link between your expectation and rational, so you can fix out how you can think about the results based on your model parameter study. Okay, how about the walking speed? Walking speed, the divided distance traveled and divide by the time it's been taken. So it's gonna be something like a t for one step, tf, and then the distance traveled, which is 2 alpha l. And these are all constants, so how your TF is going to be expressed, which is this one. So TF, you can also obtain this value from your previous solution with the final condition. And this is definitely a function of gamma and all the initial conditions. And here I can find that, oh, the time, the t, there is a condition that gamma should be should have certain value to make this term to be positive. So should be greater than alpha minus omega naught divided by the sigma. So if I draw the velocity as a function of gamma, there should be some limit line that should be greater than that value for the v2 velocity to have certain reasonable range. Also, what would be the maximum speed for rimless wheel to walk? For suppose that you have a velocity v here, and then if you draw the free body diagram, you have a gravity matching with balancing with the normal force that will generate the acceleration. So if you're only considering this inverted pendulum for upright posture, this is rotating, moving this way. So it's a centripetal acceleration. So to have those normal force to be greater so that it doesn't fly out, you should have certain constraints on that. So by solving this, you will have a maximum value is going to be a function of leg length and gravity by a square root. So maybe your maximum velocity has a certain limit. Okay, you can't really increase all the way. So that's gonna be of some reasonable reasonable result for the model. Yeah, there is a specific limit for the feasible walking speed, and you can get an impression that okay, the taller people tends to have a faster natural gait. Okay, how about the energy involved? So we know that whenever there's a collision occurs, there must be an energy loss, okay, occurred. And then how those energy loss will be related to the gait speed or parameters like a leg length or the interleg angle. One way to define the efficiency is a cost of transportation. So energy in versus the energy in divided by the weight multiplied by the distance traveled. So here, the energy in, it's you originally defined from the vehicle dynamics. So the energy in must be the gas or maybe the chemical energy in. For the human motion, it will be metabolic cost. Or for the rimless wheel, the gravity is the only energy source in here. So it's real gravitational potential energy. So for rimless wheel, the gravitational, the distance traveled is going to be 2 alpha L, the distance d, and the gravitational potential energy drop will be calculated the vertical components of the mass height changes, which is d sine gamma. So if you if you could calculate them, this is surprisingly simple, which is just sine gamma. It's only a function of the slope. So for the rimless wheel, if you have a larger slope, your cost of transportation increases due to compensate the greater collision loss at the impact. Experimental report for the cost of transportation for the automobile is somewhat very, very small, like compared to a human being, like a walking is something like 0.3. And as I said, the rimless wheel is going to be proportional to the slope. And if you have a greater slope, you'll have more costs. And then as you can see here, it'll drastically increases. Okay, so even though the slope becomes something like a triple time, this cost increase is a lot larger than that. So why is the rimless wheel so inefficient at steeper slope? we can find the answer by analyzing the energy loss during collision. So when there is a previous, like a before collision velocity mv minus, and when there is a collision force applied at the contact point, then your after collision velocity will have this vector impulse momentum relationship. So your impulse applied will be same as a vector change for the linear momentum, which is mv plus minus mv minus. Since this is a 2 alpha and this is 2 alpha as well, so and then this is a parallel to the leg length for the stance leg, with the collision. So we can have those v plus is gonna be a function of v minus cosine 2 alpha, right? So if you could calculate the energy loss, which is kinetic energy change, 1/2 mv plus square minus mv minus square, you will have a function of 1/2 m cosine 2 alpha square minus 1 v minus square, and this is same as sine square 2 alpha term with it. So for a small angle, this is approximated as something like a alpha square and v minus square, the before collision velocity square. So as you could see here, if you have a larger interleg angle, the energy loss increases as a quadratic manner for the alpha. Okay, that's why you have a no, that's intuitive, okay? And for calculating the cost of transportation, we could have weight and distance traveled as mg2 alpha L, and energy in here is to compensate the energy loss. So if you plug that in, you will end up getting this value. And then if you examining it, so this one is something like a temporal components, and this is kind of length component. So maybe you can approximate as it's gonna be proportional to the step length square and the step frequency square. So that's the cost of transportation purely analyzed based on the mechanical point of view. And maybe at some point you will wonder if the human being really does spend more energy as a quadratic manner for the step frequency or the step length. So researchers study would like to prove if this mechanical approach for the cost of transportation would hold. One popular way the biomechanist is examining cost of transportation is calculating this energy in as a chemical energy in based on the oxygen consumption. Human being use the metabolic cost by the ATP, and then oxygen is a source to provide those energy. It is used to provide the energy. So for specific human motion, examining oxygen consumption, we can estimate some proportionality how much metabolic cost has been consumed during those motions. It's one of the typical popular method to examining human metabolic cost.